this set of notes, we're going to continue our discussion of moment-generating functions. And so if you remember, one of the really useful aspects of a moment-generating function is that it acts like the fingerprint for a distribution. So if you know the moment-generating function, you can then figure out what or how a random variable is distributed. So this can be very useful if you're not sure what that distribution for that random variable is, but you do know the moment-generating function. And we'll see here in a little bit, this can also be really useful when looking at functions of random variables. But suppose that we have a moment generating function here and we want to find the probability distribution of y. So what we can do is we could look at a list of moment generating functions and see if we see one that looks similar, and then from there see if we can figure out what the distribution is. So one place that you can look is I gave earlier in the course in the announcements, there was that probability cheat sheet, and that probability cheat sheet, if you look at the very last page, has a table of distributions and their corresponding moment generating functions. Now, one word of caution here, and you've already seen this some in the class, is we do have to be careful with the distributions because there are different ways to parameterize them. And so this is kind of a good example of that. So if you look at that list of moment generating functions, you want to find one that looks somewhat similar here. And if you look, you're going to see one, you can't find one that looks exactly the same. But if you look, you will find the geometric distribution. And so if you look at the geometric distribution, you'll find that the moment generating function is equal to p to the 1 minus q e to the t. And that's defined for q e to the t less than 1. So looking at this, it looks somewhat similar. You know, down here in the denominator, we have a 1 minus a constant times e to the t, but what we're really missing is that e to the t in the numerator. And so it ends up that the geometric distribution has two common ways to parameterize it. So in that probability cheat sheet that I gave you, they use one parameterization, and if you use that parameterization, you work through it, this is the moment generating function you can get. Or if you go and you look at our notes, we use a slightly different parameterization. And so for the geometric distribution in our notes, the way that it's parameterized, if you were to work through the moment generating function, you would find that that one is p e to the t 1 minus p e to the t. So notice this parameterization does have that e to the t in the numerator. So looking at this parameterization, we can see that if p were equal to 1/2, we would have the exact same thing. So here we know that y is distributed geometric with p equal to 1/2. So I say this to be very careful. If you have a list of moment generating functions, don't forget that there are different potential parameterizations. So if you see something that looks close but not quite the same, do make sure that you look at those alternative parameterizations. The Wikipedia page for each distribution is very useful. So I would pause the video here, go have a look at the geometric distribution on Wikipedia, and you'll notice on the right-hand side, when it has the different images of what the distribution looks like, below that it has each of those parameterizations. And you can see how that moment generating function depends on which parameterization you are using. All right. So let's look at how the moment generating function can help us when finding the probability distribution of a function of random variables. And it does end up there are several techniques for finding the probability distribution function of random variables. These will be covered more in depth in 676. Here we're going to look a little bit at the method of moment generating functions. You'll see another method when we talk about sampling distributions in the future. So if x and y are two random variables with equivalent moment generating functions, in other words, m of x of t is equal to m of y of t for all t, then we can say that x and y have the same probability distribution. And so this can be really useful if it's easier to work with the moment generating functions and the probability distributions to find what those distributions are. And we're going to see a couple examples of when that would be true. So suppose that y is distributed normal with mu sigma squared, and we want to find the probability distribution of z, which is equal to y minus mu divided by sigma. So notice here we do have a function of a random variable, and in fact this is one that you've seen before. Notice what we're doing here is we're taking that random variable y and we are standardizing it. So the question here is, if y is originally distributed normal mu sigma squared, what happens to the distribution of that random variable once we standardize it? And so let's see if we can figure that out. So what we want to find here is the moment generating function of that random variable z. And so notice by definition that is equal to the expected value of e to the t z. But we know what z is equal to because we're using this transformation. So notice this is the same thing as the expected value of e to the t, and I'm just going to substitute in here what z is equal to. So to this point, I'm really only using the definition of the moment generating function. And then just to keep my notation the same, I'll make that round. All right. Here, I'm just going to expand out what's in the exponent. Okay. And, oops, sorry about that. Next, since here in the exponent we are subtracting, notice that this is equal to the expected value of e to the t divided by sigma y times e to the negative t mu divided by sigma. So this is where this idea of what is random and what is not random becomes very important. So if we look at what we have so far, remember that z was our random variable, and we set z equal to y minus mu divided by sigma. So mu and sigma are both constants. They are not random. The only piece here that is random is the y. So if we track the y as we move, notice that this piece here to the right does not contain anything that is random. So this is really just a constant. So since that's a constant, we can pull that outside of the expected value. But notice, so I still have that constant out front, but by the definition of a moment generating function, this is equal to the moment generating function of y evaluated at t divided by sigma. Okay. So the next thing we're going to do is we need to know what the moment generating function of a normal random variable is. And the reason we need that is we were given up at the top that y is distributed normal. So the moment generating function for a normal distribution, we can find that a couple different ways. We could go to Wikipedia and look that up. We could also go to your probability cheat sheet. It is the same parameterization there. So you should find that moment generating function for the normal is equal to e to the mu t plus t squared sigma squared divided by 2. And notice all of that is in the numerator, or probably in the exponent, not in the numerator, in the exponent. But notice we don't want the moment generating function of y evaluated at t. We want it evaluated at t divided by alpha. And we want that because, again, that's what we have up here. So that's going to be equal to e to the mu divided by t alpha plus t squared, divided by alpha squared, sigma squared, all divided by 2. So, therefore, remember what we were doing all the way up at the top. We started out with the moment generating function of z. So mz at t. And then we were able to show all the way down to here that was equal to e to the negative t mu divided by sigma times the moment generating function of y evaluated at t divided by alpha. So this is equal to e to the negative t mu sigma times e to the mu t divided by alpha plus t divided by alpha squared sigma squared divided by 2. And again, that is all in the exponent. And then you can show that this simplifies to e to the t squared divided by 2. But notice that this is the moment generating function for a normal 0, 1. And we can see that because if we were to come up here where we have the moment generating function for our normal written down, notice that if mu were equal to 0, this piece in the exponent would go away. We would just have 0 plus. And then if sigma were equal to 1, this would be 1. So we would just end up with e to the t divided by 2, which is exactly what we've got here. So therefore, z is distributed normal 0, 1. And so that brings us to this fact right here. All right, let's look at another example. So now we have a z, which is distributed normal 0, 1. The question is, can we find the probability distribution of z squared? So now we're going to take the random variable and we are going to square it. So here we have that u is equal to z squared. So what we're looking for is the moment generating function of u evaluated at t. So by definition, this is equal to the expected value of e to the t u. And that is equal to the expected value of e to the t z squared. Okay. Well, next thing we're going to do is we're going to use the definition of expected value. So this is equal to the integral from negative infinity to infinity, e to the t z squared. And then we are going to multiply that by 1 over the square root of 2 pi e to the negative z squared divided by 2 dz. And so you may be asking, where is this piece right here coming from? This is coming from the fact that we're looking for the expected value of a function of z squared. Remember that z is our random variable here. So we've seen previously we can find the expected value of a function of a random variable if we take that function multiplied by the PDF of that random variable. And so z is distributed normal 0, 1. So this is the PDF of a normal 0, 1. To see this, look at the PDF of a normal distribution when mu is equal to 0 and sigma squared is equal to 1. All right. Next, for that integration, we have this is equal to negative infinity to infinity, 1 over the square root of 2 pi e to the negative z squared over alpha, over 2 plus t z squared dz. So all we did was bring in that e t z squared, multiplied that through. And then notice this is equal to negative infinity to infinity, 1 over the square root of 2 pi e to the negative z squared divided by 2 times 1 plus 2t. Now, this integration looks really nasty, so we're going to do that same trick that we did last time. The question is, can we make what is inside of the integral look similar to one of our known distribution functions, since we know that if we integrate over the sample space of one of our known distribution functions, that will integrate to 1. And so we do this by multiplying by 1, but really how we get that 1 is we see what constant we need to get that to be the PDF we want, and then multiply by 1 over that constant outside of the integral so that we're only multiplying by 1. All right, so to see this, let's look at a normal density function. So remember that the normal mu sigma squared density function is as follows. It's f of y is equal to 1 over the square root of 2 pi sigma e to the negative 1 over 2 sigma squared y minus mu squared. So notice what we've got up here looks pretty similar. We just need to work with it just a little bit. So notice that it looks like a normal with mean 0 and sigma squared equal to 1 over 1 minus 2t. So, the moment generating function of u evaluated at t is equal to 1 over the square root of 1 minus 2t times the integral from negative infinity to infinity, 1 over the square root of 2 pi, the square root of 1 minus 2t e, there's a square root of 1 over 1 minus 2t there, e to the negative z squared, 2 times 1 over 1 minus 2t dz. So let's look at where these different pieces came from. So looking up here with what we had originally, we can see the 1 over the square root of 2 pi is right here. We can see that our negative z squared divided by 2 is right here. What has changed is before we had this multiply by 1 plus 2t. Here we've divided by 1 over 1 plus 2t. So the only thing we've done is dropped this into the denominator by having 1 over 1 minus 2 plus t. So that's why we were saying this looks like a normal with sigma squared equal to 1 over 1 minus 2t. Now, in order to get the constant out here so that it looks like a normal, notice in a normal distribution, the only piece we were really missing is having that 1 over sigma out here. So we've added the sigma into the denominator here, and so that's the square root of 1 over 1 minus 2t. But we also have to, on the outside, multiply by 1 over the square root of 1 minus 2t, so that we're really only multiplying by 1. So now, by doing this, what we end up with is this entire piece here is going to be equal to 1. It integrates to 1 because that is the PDF of a normal distribution. We know if we integrate a PDF over the entire sample space, that is going to be equal to 1. So we are just left with 1 over the square root of 1 minus 2t if t is less than a half. Because notice we need that so that we don't end up with an I or a 0 here in the denominator. And it ends up, if you go and you look at your list of moment generating functions, you should find that this is the moment generating function of a random variable with a chi-squared distribution with 1 degree of freedom, which is exactly what we wanted to show. Right? So this brings us to this fact. We now know that if z is distributed normal 0, 1, then z squared is going to have a chi-squared distribution with 1 degree of freedom. Right? So here's another theorem that's going to help us out. Suppose that y1 through yn are independent random variables, and here are their corresponding moment generating functions. Then if u is equal to the sum of those random variables, then the moment generating function of u is equal to the moment generating functions multiplied together. Where this is coming from, this isn't too hard to prove. This is because, remember, in a moment generating function, you're looking at e to the something. So since you're looking at e to the something, that's where you're having that change from addition to multiplication. So here, let y1 through yn be IID, normal, mu sigma squared. So notice that each of the y's has the same mean and the same sigma squared. Show that y bar is distributed normal, mu sigma squared over to n. So first thing we're going to do here, oops, is we are first going to note that the moment generating function of any of the individual yi's evaluated at t is going to be equal to e to the t mu plus sigma squared t squared divided by 2. And again, notice all of that is in the exponent. And then also note that y bar, what we're interested in, is equal to 1 over n, the sum I equals 1 to n yi, which is also equal to the sum of I equals 1 to the n 1 over n yi. So next, let's find the moment generating function of 1 over n yi. So the moment generating function of 1 over n yi evaluated at t by definition is equal to the expected value of e to the t 1 over n yi. But notice if we group together the t and the 1 over n, that is the same thing as the moment generating function of yi evaluated at 1 over n times t. And we know the moment generating function of yi, so this is going to be equal to e to the 1 over n t mu, because notice up here for the normal distribution we've got e to the t mu, so evaluated at t over n, that's going to be e to the 1 over n t mu plus sigma squared 1 over n t squared divided by 2. And so by a similar argument, here we have up at the top the moment generating function for the normal evaluated at t. Here we're evaluating at 1 over nt, so that's why we have, oops, I'm sorry, that squared should be outside. We have 1 over we have 1 over n times t, that whole quantity squared. So therefore, the moment generating function of y bar of t, using that theorem that we have up above, it's going to be equal to the moment generating function of 1 over n y1 t all the way times the moment generating function of 1 over n yn evaluated at t, which is equal to e to the 1 over n. Actually, to make this easier, I'm just going to write t over n multiplied n times. Now notice this would not be the case if those normal distributions did not all have the same mean and the same variance, but you could do something very similar. And then from here we can show that this is equal to e to the mu t, and we can see this because we've got 1 over n mu here, but we're multiplying that n times, so that's how you end up with e to the mu t plus sigma squared t squared n 2. And where that is coming from is you've got t over n squared, so the n squared comes into the denominator here, but you have that multiplied n times, so you end up with n over n squared, so you're just going to have an n in the denominator, and then of course the 2 is just there. And it ends up that this is the moment generating function of a normal with mean mu and variance sigma squared over n. And so these are some pretty common results that you see in introductory statistics, but you don't see where they actually come from. And so how we can show the distribution of these functions of random variables is by using the moment generating function. So each of these three results that you saw in this note set, you're also going to see them when we talk about sampling distributions. There's going to be a couple additional ones, and how you would arrive at those are very similar to how we've arrived at these.